Everyone, and welcome back to Activity 32. Today's lesson is 32.2, which starts on page 446 in your Springboard books, and we will be working more with vectors and their operations. So in the last lesson, we talked about with a vector, you always start at the tail and end at the head. It's a direction and a length. So if we look here in the diagram provided on page 446, we have a 10-inch segment and a 13-inch segment. And if we start at the tail and go to the head of this, we talked about yesterday that the component form is written in a bracket sense, a comma B. And in this case, we would have to move to the right 6 and up 8 from 0, 0. It's a vector in standard position. This is U, this is V. And we would represent this in component form then as 6, 8. And again, if this was a true vector, when we were graphing, we would make sure we are graphing this with an arrow, and again to the right 6 and up 8. Well, if the second piece here is going to represent vector V, vector V starts at 6, 8, but then moves to 18, 3. So it went to the right 12 and down 5, so represented by 12, -5 in this component form. So again, we would show this with the head and tail represented as the arrow, right? And again, this would be U, this would be V graphically. What we notice is if we start at the tail of vector U and end up at the head of vector V, so our original starting point and our final ending point, what we see is that this is going to actually be a combination of U and V. Now notice this one's a standard position, and this new one would be 18, 3 would be the movement, would be the component form of this newly created vector. Now, what you might notice between our newly created component form and U and V is that these are added together, this new vector. So what we notice is that U and V together, it's the sum of the A components and then the sum of the B components to get our final new answer. All right, so this is an example of segment addition. It's not segment addition, excuse me, vector addition, where you add up the components of the original vectors to get your final answer, and they're also showing these graphically as well, like we did in the last problem. So this next part, we're going to just look at this the symbolically as opposed to geometrically, but again, to show vector S plus vector T, we are going to add again the two A components together as well as the two B components for a final answer of 1, 5. Okay? And same thing for Q and R. You would add the two components together. We would have -6 plus 8 are two A components. Add the two B components. We end up with a final answer of 2, -10 for our component there. Now, with vector addition, a couple of things. When we add, if we would take vectors U plus vector V or vector V plus vector U, we would have the same answer. So again, kind of looking back here, this is going to show commutative property because whether we're doing 4 plus -3 or -3 plus 4, we get 1, 1 plus 4, or 4 plus 1 is 5. So we see that vector addition is in fact commutative. Okay. Now, an important thing also to be able to look at, though, is thinking about our magnitudes. So if we go back to the beginning when we were talking about vector U and vector V, right? If we found the magnitudes of these, remember magnitude is represented by those absolute value bars. A reminder, absolute value, the magnitude is found by taking square root of A squared plus B squared, right? So square root of 36 plus 64 is 100, right? So we would have 10 as our magnitude. And if we looked at vector V, the component form 12 squared and 5 squared would be 13. So if we added those two together, we would have 23, right? Well, if we try to find the component form of vector u plus vector v, so in this case, 18 squared plus 3 squared, 18 squared is plus 3 squared is the square root of 333, which is not 23, right? That we got up above. This would be 18.2. So what we see here is that we have to be careful because adding back together u plus v is not the same thing as taking the individual magnitudes of u and v and adding them together. So something we'll see here, the magnitudes added together is not the same thing as taking those individual magnitudes and adding them together. Okay, so that was just an example to look at them, but they have, you could test it out with the others as well. Now, the next piece of this then at the bottom of page 447 is talking about the additive inverse. And basically the additive inverse is basically kind of think of, the negative or adding the, what could we add to the original to make it even out. So what we see here is if we're talking about vector W, the additive inverse of vector W is going to be the opposite signs of what W was. So instead of being -2 and 5, it's now +2 and -5. And again, thinking about what would equivalent it back out so that it's kind of equaling 0. Okay, or think distribute a negative is another way of looking at that. Now, if we look at the next page, let's skip 9 because again, I'm not focusing graphically, but if we look at the component form then of v minus w, that would be like taking the addition of v and the additive inverse negative w. So 3 plus 2, again, if we look here, and 4 plus -5. So we get a final answer of 5, -1. And again, we would see that if we did the individuals and then where it connected as well graphically, right? If we graphed each of these and then looked at their resulting vector, it would move 5 to the right and down 1. Now, again, this is resulting from looking at v plus negative w, right? It's the same idea as looking at this, v minus w. So you have to kind of be careful, kind of like when you distribute in a polynomial. Let's say we had 3 plus 2 minus 4 plus 5 or something like this. You'd have to distribute the negative. It's kind of that same concept with vectors. You want to be careful that you distribute the negative when you're looking at vector subtraction. Okay, it's the same idea. Is making sure you distribute the negative. Okay. Now let's see. So jumping down, again, if we practice here, let's skip the geometric representation. But if we just look at these s minus t, again, you want to be careful because you want to make sure you look at t when you subtract as minus the 1. And then when we're looking at the b components, 2 minus -4. Okay, so just be careful. We end up with -3, 6. And then same thing with our second example. And this time we're doing t minus s. Notice it's not going to be commutative this time because if we do the a components, 1 minus -2. Again, order is very important this time. And then we have -4 minus 2 for a final answer of 3, -6. So again, not commutative, unlike the addition, which was subtraction. You got to be careful. Order is important with subtraction. So note that. All right. Now, one last thing we have here is vector multiplication, if you will, where we represent the multiplying by a singular number. So instead of adding 3 times, multiply it by 3. So it's adding that same vector u 3 times is the same thing as multiplying it by this scalar out front, which would be 3 this time. So it's the same idea as distributing a 3 to both pieces of the original component form, because our final vector was 6, 3, which was 2, 1 times 3. Okay, so whenever you are multiplying by a scalar, both pieces get that component, right? So if we're looking at v by scalar of 2, it would be negative 4, 8, because we are distributing here the 2. In the next one, if we are looking for 3 times w, we would multiply both of these by a 3, so negative 9, negative 3. And then last but not least, negative 2 times w is distributing that negative there. So we would have positive 6 and then positive 2 as our final answer there. So again, just distributing that. Okay, so that's all we have so far with our vector operations. We will definitely be working more with addition, subtraction, and scalar multiplication moving forward. Thanks for watching.